Good afternoon, Professor, colleagues. I'm going to present you a heat transfer problem. It's a heat conduction in a plane wall problem. The wall of a passive solar collector consists of L-thickness phase-change material, PCM, enclosed between two supporting structural surfaces. Assume a steady-state condition for the absorption of solar radiation on a surface to maintain its temperature, Ts1, above the melting temperature of the PCM. The liquid and solid portions of the PCM are divided by a narrow vertical interface. The liquid has a core temperature of Tm and is characterized by a recirculating flow moved by buoyancy that maintains the same convection coefficient Hm and at its interfaces with the surface S1 and the solid. Consider conditions for which the net radiation flux is Q-rad equals 1000 watt per square meter. The ambient temperatures and the convection coefficients are T infinite 1, T infinite 2 are equals, and it's equals to 20 degrees Celsius, and H1 equals H2 equals 20 watt per square meter Kelvin. The temperature and convection coefficient of the PCM liquid are Tm 50 degrees Celsius and Hm equals 10 watt per square meter Kelvin, and the thermal conductivity of the PCM solid is Ks equals to 0.5 watt per meter Kelvin. Evaluate the temperature of the surface Ts1 and what is the thickness of the liquid layer. Find the temperature Ts2. So let's see. This is the solar collector wall representation, and this is a scheme of this solar collector wall. And let's go to the solution. We have to do three assumptions: a stable state, one-dimensional conduction, and that there is now power generation. To carry out the problem, we have the thermal circuit, the equivalent electrical circuit, as you can see there, no? From where we find the heat fluxes Q1 and Q2, and after replacing, we have that Q1 it's equals to 20 Ts1 minus 400, and Q2 10 Ts1 minus 500. And this is equation 1, equation 2, and from here to here we have that Q2 is also equals to, after replacing, Ts1 minus 20 divided by 0.25 plus 2 times Ls. And for an energy balance, we have that energy in is equals to energy out, and this means that Q red equals to Q1 plus Q2. So of 1 and 2, equation 1 and equation 2, we have that 1000 equals to 20 Ts1 minus 400 plus 10 Ts1, 10 times Ts1 minus 500, and we get that Ts1 equals to 63.33 degrees Celsius. Replacing in 2, we get that Q2 equals to 133.33 watt per square meter. And in 3, remember equation 3, we have the ls equals to 0.0375 meters. And finally for these two, remember this sum. After replacing, we have that TS2 is 26.67 degrees Celsius approximately. And this is all. Thanks.